May I introduce myself in a quick words?
Yeah.
So
Please.
first of all, I forget also to thank the organizers. So thank you for the organization. My name is Sajanthan Sekaran, and I'm a second-year PhD student under the supervision of Emmanuel Fromager. And I'm mainly working on embedding techniques, and we are trying to push it to its limits and see if we are going to apply it in quantum chemistry really soon. So yeah, that's all for me. So yeah, the exact title of my presentation is the development of new embedding methods for strongly correlated systems. So a quick word about my collaborator. So my supervisor, Professor Emmanuel Fromager, and his long date friend, Masahisa Tsushisu, who is a physicist in Japan, and Mathieu Sobaner, who is a researcher in Montpellier and introduced us to the household transformation I will talk about later. So in quantum embedding, what we would like to do is to replace the study of the full system, which is in general too expensive to solve, by smaller fragments. So in condensed matter physics, in general, we have this infinite replica of the unit cells. And in quantum chemistry, we have this exponential growth of the wave function expansion for a given base of depending on the basis. So what we would like to do is to take, for example, in condensed matter physics, one unit cell that we want to study, and we will call it the impurity and try to find the best representative of the rest of the system, which will be denoted the path. Again, in quantum chemistry, if we take a molecule, we can fragment it into several parts, and we'll take one of it, which will be the impurity, and then try to find the best representative for the rest of the system. So this new system, which will be composed of the impurity and the bath, will be the cluster. And we will end up with this embedded Schrödinger equation, which is naturally easier to solve. So at the end, what we would like is to have a local evaluation of this, or the reduced density matrices, but from the cluster. As I told you, the expectation value of the 1 and 2 body operators is too expensive numerically within the full wave function. So we'll try to approximate them with this embedded wave function. And at the end, we can have access to local properties such as the pulsate energy or the double occupation. So given that this seminar series are organized by researchers in Rutgers, I cannot talk about embedding without mentioning the work of Kotliar and George about dynamical mean field theory, in where actually in the most simple case, they will take one molecular orbital, one atom, which will be the impurity, and then they will connect it to an infinite number of sites with non-interacting electrons. So in some way, this impurity will be connected to a bath of electrons. So the main variables that we use will be the green function, the one particle green function, and which is a frequency-dependent object. So they could study the evolution of the states of the impurity through time. And the self-consistency condition will be that the green function of this impurity matches the local green function of the lattice. So we can see here that we didn't really reduce the size of the system because we still have this infinite number of sites for the bath. So this was bypassed by the density matrix embedding theory by Chan and Knizia, where actually they started from the full system and decomposed it into several parts. So in the most simple case, they will have one atom for the fragment, so one molecular orbital, and then they will have all the remaining, which will be the environment and not the bath. You have to be careful. So the main variables they will use is the wave function, and they're going to express it in terms of the Hilbert spaces of the states of the fragments A and the environment B. And if we take a single molecular orbital, this fragment will have 4 different states. It's the empty one, the singly occupied with spin up, the other one with spin down, and the doubly occupied. And this one will contain a lot of different states. So what they did actually is to apply the singular value decomposition to this coefficient tensor. And it allows them to rewrite these states in a new basis thanks to these U and V unitary matrices. And what is really nice is that actually through this singular value decomposition, you can see that the summation here runs only in between the minimum of the number of states of A or B. So the environment will be reduced to the same number of states of A. So here we see that we are really reduced the size of the bus. The problem is actually, in order to have this beautiful decomposition, we have to have access to the full many-body wave function. And of course, we don't have it. So even despite its elegance and simplicity, actually it hides some complexity. So I have to mention also that this bus now is a many-body states, but I will come back to it later. So what we try to do with Emmanuel, Fromager and the other collaborators is to rephrase and extend the MET as a functional of the reduced density matrix. And we called our approach householder transformed density matrix embedding theory. So we started from a lattice model. So I will just give a few words about the urban model. Philip already introduced it. So we have two parameters which are in competition. The T parameter, which is the hopping, or the equivalent to the kinetic energy, and allows electrons to flow from one side to another. And if two electrons are on the same side, then they will repel each other through this U parameter. So we have naturally two limits. If the kinetic energy is really large, then the electrons can flow easily from one side to another, and we will have this delocalized picture, which can reflect a metallic state. On the other limit, if the U is really large compared to the kinetic energy, in some density regime, the electrons will remain localized, and it could reflect an insulating state. So at the end, even if it's a really simple model, we can see that it already contains a lot of physics, and especially this transition from the metallic state to the insulator one. So as I mentioned, we based our embedding theory on the one electron reduced density matrix. But the question is now, how can we go from the full system to something which is closer, smaller? So this is where we use this householder transformation. So it's a unitary transformation, and sadly, I don't have enough time to talk about it today, but you will find all the information you need in both these papers. So if we start from our density matrix in the lattice representation, actually we can build this transformation matrix only thanks to the first column of the density matrix. And so yeah, again, the information will be in the paper. And if we apply this transformation matrix, transformation on the density matrix, we will end up with a new representation. And the really nice advantage we have by using the reduced density matrix is that we can clearly see how we cut or separate the orbital space. And in the new representation, actually, we see that we have something that we refer to as the householder cluster. Then there is a second part, which we called the householder environment. And connecting these two, there will be the buffer sector. I mean, this is our notation. And what is really nice with this householder transformation is that if we apply it to a mean field or non-interacting density matrix, in which case it will fulfill this idempotency condition, then by applying it, we will end up with a closed and disconnected householder cluster. As you can see, there is no more this buffer section. And this cluster will contain exactly 2 electrons. So depending on if we start from a correlated or not density matrix, we will end up with one of these 2 cases. And we also find an extension to multiple impurities thanks to this paper, which describes the block householder transformation. And actually, we can select 2 impurities or 3 or more, and it will increase the size of this householder cluster with 2 impurities and 2 bars, etc. And actually, we find again the same properties as for the 1 impurity, in which if we start with a non-interacting density matrix and apply this block householder transformation, we will also end up with this total disconnection between the 2 subsystems. So what we did is we started from this non-interacting density matrix and we applied the householder transformation. And we decided to only focus on this householder dimer, which is composed of the impurity and the bus. And what is, again, another really nice feature of this transformation is that this impurity site is unchanged, and we can prove it really easily. And you can see here that this bus site is now a linear combination of all the remaining sites. So in some sense, you will gather information from the rest of the system and become something like a superatom. So we were not expecting that, but actually we find similar results as density matrix embedding theory, and we were really happy. And one way to prove it was actually to diagonalize this Householder cluster, and we end up with one molecular orbital, one occupied molecular orbitals, which is a linear combination of the impurity and the bass, and which is the only one who has an overlap with the impurity here. So we were surprised, but really happy. And another really nice advantage or feature of this Householder transformation, if you remember before I told you that in density matrix theory, embedding theory, the bass actually was a many-body states, but in our case, it's a single orbital. So it allows the use of existing exact diagonalization method, such as configuration interaction and all the rest. So at the end, there is a drastic simplification because we started from the full system and ended up with this 2-atom plus superatom subsystem. If we look at the results, once we had this Householder dimer, we introduced interaction on the impurity site. And what we can see on the impurity site occupation is that it's not following the exact one. This is not a new result. And we see that the number of electrons is decreasing. So, okay, we decided to just have a look, and we plotted the per site energy as a function of the electronic density in the half field case. And here in black, you have the exact results, and you can see that the results when the density of the impurity is not good are really bad here. So what we have to do is to introduce a chemical potential on the impurity site in order to get back the correct density. And once we have corrected this, we can see that now the results are really close to the exact one. So we see how important it is to have a correct density on the impurity site or the system we are studying. And it's maybe not obvious, but in some ways there is this connection with DFT, because what we did by adding this chemical potential is to get back the correct density. So in some way it is connected to the Hartree exchange correlation in the constant DFT. But I will come back to this later. So now we plotted the per site energy as a function of the density of the system for a strongly correlated case. And here again in black, you have the exact results, and you can see that even if the overall shape are quite good, there are still some discrepancies. And by increasing the number of impurity, actually, we are getting closer to the exact results for a large density domain. And we also have the same properties, I mean, the same behavior when we studied the double occupation of the impurity site as a function of the electronic repulsion, again, for the half field case. Here in black, we'll have the exact results. And you see that when we go from one impurity to two and more, we are getting closer to the exact one. So now I still have, I think, a little time to talk about the connection we want to do with DFT. Is if we come back to what we did, actually, we started from a non-interacting lattice system with a fixed number of electrons. And given that it was a uniform system, this external potential actually was the chemical potential. So the question is, how can we be more accurate? And one way could be to rethink the system as a Kohn-Sham system, where we will add this Hartree exchange correlation potential and let the number of electrons fluctuates. So once we have this, we can also have this Householder cluster by the same transformation. And as I told you before, there is this decrease of the occupation number when we add the interaction on the impurity site. And we correct it by adding this chemical potential. And in this case, it will play the same role again as the Hartree exchange correlation. So we can find that there is a connection between these two systems. And actually, we have to map the occupation number. It is not new. Already people worked on this, and you can find the papers here. But by finding the correct Hartree exchange correlation potential, such that both of the system will give the same density. So, and there is this clear self-consistency condition. So work is in progress, and we'll see what's happening. And in some way, it's also funny because it's like a static and frequency independent version of the dynamical mean field theory. Because in the latter, actually, you will find the impurity green functions, and then you can find the self-energy of the impurity. that you will propagate through the full system and then get back the vice field and then get another impurity green function, etc. So yeah, work is in progress and we'll see. So to conclude, we have seen that we have a new embedding method, which is based on the one-electron density matrix. We recovered DMET results with a simpler formulation. Extension to multiple impurities are possible, and it will allow us to apply our method to quantum chemistry and small molecules. So I want to thank you all again for your attention and all the members of the lab and the FLC for the funding. Thank you.